it's circular, it has a diameter, then we've got to worry about, well, what's the area of a circle? So the area of a circle we know is pi r squared. And then the height is just the other dimension of height. So if we take pi r squared times the height, we'll be able to find out the volume of this tank. So we take pi. Now, the radius, the diameter was 10 feet, so the radius is 5 feet. So we put in 5 foot in here for the radius, square it, and then we multiply by the height, which was 10 feet. And we'll end up here with 5 squared, which is 25, times pi times 10. And notice our units, our foot will be squared, and then it's going to be multiplied by another square, or by another linear, and it'll turn out to be cubic feet, which we know cubic feet is a volume. So if we take 25 times our pi, which I'm just going to use 3.14, you can push your pi key if you want to, and you'll get a little bit different answer, times 10, and this turns out to be 785 cubic foot is the volume of the tank. That still doesn't help us get to how long will it take to fill a tank, because we need to know something about gallons. We either need to convert those gallons into cubic feet, or we need to calculate the tank cubic feet into gallons. And I personally say, well, I'd like my students to start to know, well, what's a 10-foot diameter cylindrical tank by 10 foot tall? You know, kind of how many gallons is that? So we're going to find out how many gallons are in this tank and then work from there. Now, with unit conversions, you can actually do all that right in a railroad track. I know a lot of you say, well, at this point I can handle it. I can convert to the volume of the tank and then convert into minutes or whatever, but let's just do it in a railroad track and do it all at once. We know that the question was, we wanted time, so we put 1 minute at the top, because the only thing we had time, we now know this was 785 cubic foot, and we know gallons per minute, and the only time factor we had in here is minutes. So 1 minute is equal to 75 gallons. That's what the pump puts out. Now at this point, what do we know about gallons? Well, we don't know anything about gallons, but we do know that the tank is cubic foot, so we say, well, we know there's a conversion between cubic foot and gallons, that 1 cubic foot you have memorized is equal to 7.5 gallons. Pretty amazing, isn't it? You think about it for a second. 1 gallon of milk, but see, 1 gallon of milk doesn't even come close to measuring out to 1 cubic foot. 1 cubic foot is 1 foot times 1 foot times 1 foot, and it actually, you can fit 7.5 gallons of any liquid into a cubic foot. So we have the conversion of 7.5 gallons in 1 cubic foot, and those will cross out nicely. And now we know how, for 1 minute, how many cubic foot we could, or how many minutes it'd take to pump 1 cubic foot, but we need to pump 785 cubic feet. And since I can sit here and look at this and say, well, we'll just leave it that way. All right, that's fine. And so now our cubic foot crosses out. So we got 785 times 7.5 times 1 and divide by 75. And we get 78.5 minutes. It would be how long it would take that pump to do it. If we divide by 60 and find out how many hours, that's 1.31 hours. And how many gallons is that tank? We didn't do that, but we can quickly take care of that. We can say we got 785 cubic feet, and 1 cubic foot is equal to 7.5 gallons. And so 785 times 7.5, that's a good-sized tank, 508 gallons. So getting close to 6,000 gallons. So again, we have a lot of processes like this in the nuclear facilities where we're pumping water so many gallons per minute. We've got something to fill We want to kind of have an idea how long it's going to take to fill that. There's sometimes we're worried about eroding the pipe, and we can start talking about, well, for certain speeds of flow, how fast is it going to flow through the tank pipe? How much power is it going to take? There's a lot of different things we can do with these problems, but this gives you a basic idea of how to calculate both rectangular volumes and probably the biggest volume you have out there to calculate. We have a lot of cylindrical tanks. The final volume that we have is for some of our gases, we have spherical tanks. So let's just investigate that for a second and find out what would happen as we look at radioactivity, a radioactive gas that's stored in a spherical tank. You say spherical, what's that again, Bruce? Spherical is just like a basketball. You put air into a basketball, you've put it in a spherical tank. And so why would we use a spherical tank for gases? Because when all that pressure is going out in every side, it's we can use the least amount of material and the least strength of materials to hold the gas back and hold the most gas. So it turns out to be very economical for us. So if we're going to have a spherical tank, say we have a spherical tank and it happens to be out there and it's 20 foot in diameter. And if it's spherical, it's 20 foot that way, it's 20 foot that way. It's 20 foot any way you can draw the arrows, right? It's a basketball. And it's 20 foot across. And let's say that we're storing some radioactive gas in there. And right now, it happens to be a gas, and we just took a sample of it, and we're going to say the gas sample in there came out as 1.5 times 10 to the negative fourth microcuries per milliliter at time right now. And let's say that this radioactive gas has a half-life equal to 2.4 days.